Good morning. Welcome to MDS Gurukul channel. How are you? I hope you and the member of your family will be healthy and happy. My request to you, please subscribe this channel and also share video to your friend circle. Today I am going to start a new lesson 1.4. But first let me solve the question that I gave you for practice. First question of your practice is, first question, prove that the following are irrational. Question number 1a, 7 root 5. Okay, now solve. The solution 1a. Let us assume to the contrary that 7 root 5 is rational. Therefore 7 root 5 is equal to a by b, where a and b does not equal to 0 are integers and co-prime. Implies 7 root 5 is equal to a by b. Implies 7 is here, 7 is multiplied by root 5. So when 7 go to the other side, then 7 multiply, then the other side it in the portion division. Okay, implied root 5 is equal to a by 7b. Here 7 is in multiplication, but here is 7 is in division. Okay, now I write, since 7 a and b are integers, a by 7b is rational. Therefore a by 7b is rational, and show root 5 is rational. But this contradicts the fact that root 5 is irrational. I know that root 5 is irrational. This contradiction has arisen because of our incorrect assumption that 7 root 5 is rational. Hence 7 root 5 is irrational. Proved. Question number B. Again solve. 3 root 2 is rational. Okay. Question number 2. Solution. 1b. Let us assume to the contrary that 3 root 2 is rational. Therefore 3 root 2 is equal to a by b, where a and b are integers and co-prime. Implies 3 root 2 is equal to a by b. Implies root 2 is equal to a by 3b, because 3 is in other side, 3 here 3 is multiplied by root 2, so the 3 is gone to the other side, then multiplication is gone to the other side, go to the other side, then division. Okay, so I write root 2 is equal to a by 3a. Since 3a and b are integers, therefore a by 3b is rational. And show root 2 is rational. But this contradicts the fact that root 2 is irrational. This contradiction has a reason because of our incorrect assumption that 3 root 2 is rational. Hence 3 root 2 is irrational. Proved. The next question, 1c. C 6 plus root 2 is proof 6 plus root 2 is irrational. Okay. Solution 3. One C. Let us assume to the contrary that 6 plus root 2 is rational. Therefore 6 plus root 2 is equal to a by b, where a and b are integers and coprime. Here one thing is left, coprime, and b does not equal to 0. Okay. And b does not equal to 0. Implies 6 plus root 2 is equal to a by b. Implies here 6 is in the form of add, then the 6 go to other side, then the sign is negative. Okay. Implied root 2 is equal to a by b minus 6. Here 6 is the symbol of 6 is positive, other side the symbol of 6 is negative. Is equal to LCM is equal to b, then a minus 6b. When you subtract by a rational, subtraction of rational number, then I get a minus 6b by b. Okay. Now again write, since six a and b are integers, a minus 6b by b is rational, and so root 2 is rational. But I know that root 2 is irrational, but this contradicts the fact that root 2 is irrational. This contradiction has a reason because of our incorrect assumption that 6 plus root 2 is rational. Therefore, hence 6 plus root 2 is irrational. Proved. Okay, the next 5 minus root 3 d. Solution 1d. Let us assume to the contrary that 5 minus root 3 is rational. Therefore, 5 minus root 3 is equal to a by b, where a and b does not equal to 0 are integers and coprime. Implies 5 minus root 3 is equal to a by b. Okay, implies minus interchange, minus 3 go to the other side and a plus b come to the other side. 5 a by b come to left side, then minus a by b is equal to minus 3 come to right side, then root 3. Implies LCM is equal to b, then 5b minus a is equal to root 3. Implies interchange, root 3 is equal to rotate 5b minus a by b. Okay, since 5a and b are integers, then 5b minus a by b is rational, and so root 3 is rational. But this contradicts the fact that root 3 is irrational. This contradiction has arisen because of our incorrect assumption that 5 minus root 3 is rational. So I conclude that 5 minus root 3 is irrational. Okay, proved. Now I start exercise 1.4, but first discuss on some term. Okay, in this chapter the two term, first terminating decimal and second non-terminating decimal, non-terminating repeating decimal. Okay, in your book there are 3 theorem before this exercise 1.4. Theorem 1.5, theorem 1.6 and theorem 1.7. Now I discuss first theorem 1.5. Okay, theorem 1.5. According to this theorem, if x is a rational number and whose decimal expansion terminates, it means that when I divided numerator, okay, numerator by denominator, then I get remainder 0, or I also write x is equal to p by q, because any rational number in the form of p by q. I cannot write a by b. Okay, so then expression of x, decimal expression of x terminates, it means that getting the p is divided by q, then I get remainder 0. Getting 0 is called terminates. Okay, then x can be expressed in the form of p by q, where p and q are coprime and q does not equal to 0, and the prime factorization of q is of the form of 2 to the power m into 5 to the power n, where m and n are non-negative integers. Hence m and n are whole number. Okay, it means that suppose that, for example, q is the form of 2 to the power m into 5 to the power n. Okay, the prime factorization of q. For example, according to the theorem, suppose a number is given for you 0.15. okay, then I write this in the form of p by q, then I get 15 by 100. Why 100? Because the point given 1 and after point there are 2 digits, so I put 20. Now getting a simplest form, 5 3 ja 15 and 5 2 ja 10, 0. okay, is equal to 3 by 20. So the number given 0.15, the form I write this number in the form of p by q, then I get 3 by 20. Then q, here q is equal to p by q, here q is equal to 20. The prime factorization of 20 is equal to 2 into 5 is equal to 2 to the power 2 into 5 to the power 1. It means that the 0.5 is written in the format 2 to the power 2 into 5 to the power 1. It means 2 to the power m into 5 to the n. So this is the theorem 1.5 say any number is terminated decimal express, any number in the form of terminating decimal, then it is written by p by q, in the form of p by q, and get the prime factorization of q is in the form of 2 to the power m into 5 to the power n. Theorem 1.6. This theorem is inverse of theorem 1.5. According to this theorem, if x is equal to p by q, be a rational number such that the prime factorization of q is of the form 2k power n into 5k, 2k power m into 5k power n, where m and n are non-negative integer, that is a whole number, then x has a decimal expression which terminates. It means that if q is the, here say terminate x, if any rational number in the form of decimal expression terminate, then the prime factorization of q is 2 to the power m into 5. But here say if q, the prime factorization of q is equal to 2 to the power m into 5 to the n, then the decimal expression of this rational number is terminates. Okay, for example, suppose I write 3 by 20. Okay, when I divided is equal to p by q, the prime factorization of q is equal to 20, the prime factorization of 20 is equal to 2 into 2 into 5. Okay, it means 2 to the power 2 into 5 to the power 1. This means that the number, the prime number 3 by 20, the decimal expression of this number, now 3 is divided by 20, then I get 0.01 10 0 25 100. It means that the decimal expression 3 by 2 in 20 is equal to 0.15. Okay, so this is proof that the prime factorization of q in the form of 2 to the power m into 5 to the power n, then the decimal expression of this number is terminates. Matlab, it means that we are getting the remainder 0. Okay, the next theorem 1.7. This theorem said if x is equal to p by q and q, the prime factorization of q does not in the form of 2 to the power m into 5 to the power n, then this number is non-terminating repeating. It means that the decimal expression of this number, of this rational number, is non-terminating repeating. It means that recurring. For example, one by 3. Now I divide 1 by 3. 0.033910. It means in each and every time I get remainder 1. Here 1. Okay, every time I get remainder 1. Okay, so I write 0.333 is equal to 0.3 to the power recurring. Recurring means the number, same digit come again and again. So this is not completely, this here not I am getting remainder 0, I am getting remainder 1 in each, here also, here also. Okay, so the 3 is not the form of 2 to the power m into 5 to the power n. Therefore this number is non-terminating repeating number. Okay, now I have come to the exercise 1.4. okay, question number 1. Without actual performing the long division, state whether the following rational numbers will have a terminating decimal expression or non-terminating repeating decimal expression. Okay, the first question. Solution 1. 13 by 3125. First we see that 13 by 3125 is in simplest form. How can I know given rational number is in simplest form or not? The simple method is find HCF of numerator and denominator. If HCF of numerator and denominator is 1, then given rational number is in simplest form. If HCF of numerator and denominator is not equal to 1, then given rational number is in simplest form. Okay, if not in simplest form, then we divide numerator and denominator by HCF. Okay, the rest rational number is in the simplest form. Okay, now check this rational number is in simplest form or not. Then first we find HCF of 13 and 3125. Okay, 13 divided by 3125 divided by 13. Okay, 13 to 26 5 2, 13 4 52, 5 come, then 13 is not gone to in any, 13 is not 13 1 13 here, not 5 is less than 13, so we put 0. Okay, now 5 13 is again 13 is divided by 5, then 5 to the 10, 3 5 313 2 3 212 1 2 1 2 2. Okay, the HCF is 1. HCF is equal to 1. Okay, so this number is in simplest form. Okay, now again, without actually performing the long division, how can I get this rational number is in will have a terminated decimal expression or not? Okay, then according to the theorem 1.6, here Q is equal to 3,125. Now getting prime factor of 3,125. Okay, factorize them. 5 6 2 and 5. Okay, again 5 1 2 5, again 5 25, again 5 5. Here 5 is 1 2 3 4 5 times. Okay, the 5 to 5 is equal to 2 to the power 0 and 5 to the power 5. This is the form of p by p 2 to the power m into 5 to the power n. Okay, so this number is the form of 2 to the power m into 5 to the power n. So this rational number is a terminating decimal expression. Okay, terminating decimal expression, terminating decimal. Okay, now similarly the next other question, next 9 question for your practice. Okay, you practice this number, then the next day in next video I solve the next question. Okay, that's all. Thank you. Good night.